Hello, welcome to the Berkeley Seminar. I'm very excited to welcome Kris to speak today. Kris is a wonderful team member, and one of the things I really enjoy about Kris is he and I seem to agree on something, but we don't really know exactly what it is. But often as we have these discussions at Topos, and there seems to be this sort of view that is common in, I don't know, amongst computer scientists, amongst STEM people, of like semantics and how language works, and it's clearly been very effective and a really important part of the subject. But there's something that's important to us that it often doesn't quite seem to capture, and I can't really name what it is. But Kris has been working on at least the beginnings of this, and I'm excited that he's now inviting us all into this realm of thought he's been exploring, and I hope we can all explore it with him.
Great.
So thank you, Kris.
Thank you, Brendan. Yeah, I hope I can figure out why we feel like we're allies. And yeah, so I should say that this is really coming out of left field, so I'm sad that I won't be able to do adequate. I mean, this is kind of a hopeless effort to try to bring a really big world picture without any sort of prereqs and really work from the beginning. So I'm going to try to get as much as I can, and hopefully your questions will guide to the most interesting things to explore. I only want to take 3 minutes to do motivation because a lot of the feedback I've gotten is just jump into the math as fast as possible. So I think that this subject matter is relevant to formal conceptual interoperable modeling. In particular, that formal and conceptual there can be a tension there. And that tension we start to realize when we start to see there's a distinction between formal concepts and informal or material concepts. So what are material concepts? We sometimes can forget that they exist when we're doing math. Material concepts, they come with inferences that are context sensitive. So it's part of knowing what bird means that from something being a bird that you take it to fly in the absence of any other context. And it's also part of bird that in the context of it's a penguin too, that you don't take it to fly. And there's a sort of attitude which says, okay, well then your first inference was just a bad one. You shouldn't have made that, and you secretly meant this other inference, which was if it's a bird and it's not a penguin. But taking our ordinary notion of what a good reason is at face value would mean that we're kind of at odds with these properties of logical consequence relations that are very standard for something to even be called a consequence relation at all. In particular, when you add more premises, you derive more conclusions, consequences, and when you have the consequences of the consequences, those must have been secretly consequences all along. But these are actually really absurd when you try to apply them to the actual concepts and inferences that we trade in day to day. Bird, as described above, just can't be represented at all. And sometimes probability theory is introduced to try to make sense of these issues. So we might say, what I secretly meant by it's a bird, so it flies, was conditioned on it being a bird. It's likely that it flies. But this is really a stopgap, and I can talk about why that doesn't actually solve this problem. Something else that I think is a tension is that formal logic studies concepts that are characterized by fixed truth conditions. So I might say like a bird is something of this phylum, and it has these properties maybe. And when we try to characterize meaning in terms of fixed truth conditions, we're actually seduced into thinking that there exists a fixed thing, such as the consequences of gamma at all. But in practice, when we actually use our concepts, it actually changes those concepts, and it changes what the consequences are. We might have some, particularly you might think in moral theory, we have some moral concepts, and by actually applying them, we change our understanding of ourselves in morality. So real material concepts actually have this weird property that you can't just specify the definitions and then see what follows, but actually using the definitions can change the definitions. Of course, that's utter chaos if you're trying to do math or science, and so we really like our logical concepts because they allow us to, as Sophie says, fix the frame and then negotiate the content. But it's pathological to think all of our concepts must be like that, otherwise they are inadequate concepts. They're not real concepts. They're the shadow of a real concept. So we want to have a type of math that actually allows us to treat both logical and non-logical vocabulary. And importantly, it should engage with logic. It should understand logic as special and having these great properties that allow us to crystallize thought patterns, as David says, or coordinate or have legibility. So it's great, and the math I'm going to present actually has a fully articulated position of like what demarcates logical vocabulary, and what it is something that allows you to get legibility. And there's also a lot of parallels with applied category theory. I put that in the abstract, but I might not be able to get to all of those parallels. Okay, so I'll skip my slightly longer motivation and jump into the math.
Wait, can we pause first just to see if anyone wants us to pause?
Yeah. Also, you should interrupt me if something doesn't make sense. So yeah, this was supposed to be a very fast overview of motivations. I do want to get to the math, but I also don't want, if anything sounded crazy, I don't want you to think it's crazy. I want you to be excited to say, what kind of formalism could actually make sense of a non-logical, a material concept?
Could you give me an example of like non-logical concept?
Yeah. So logical concepts are these ones that we sort of create in a laboratory, and they're, by construction, their semantics is, we fix what their semantics is by fiat. But on the other hand, non-logical concepts might be things like, cat and red and electron, and the idea is that we don't actually stipulate what the semantics are those ahead of time. We actually could learn that we were wrong. We might have a putative definition of what a cat is, but we might learn actually that we were wrong. And even, I'll save the more radical examples, but so you could think of material concept as ordinary concept. Ordinary language concept.
Are there any real examples of logical concepts, or only almost examples that we try to make behave that way?
Yeah, so I do think that like trying to make like a hard distinction between these two things that like really partitions all concept into the formal ones and the non-formal ones, I don't think that will work. But clearly conjunction is in the formal side of things. And for the purposes of doing this kind of work, I will take it to be a purely formal concept. But yeah, that's a good, sneaky question. Yes, Dana?
I don't know if this fits in with your kind of sociology here, but in the beginning, topological spaces were like the real numbers.
Mm-hmm.
And then much later, people found there are all kinds of crazy topological spaces, and that changed what we use them
That's a
for.
perfect I said I was going to hold back from the radical examples, but I do think even mathematical concepts are not determined by fixed truth conditions. That as we did more geometry, we found out that our notion of maybe what a triangle was could have changed. Because before it was essential to triangles that they had 180 degrees internally, and then it no longer was true. So yeah, I think that's actually a very, very insightful thing. But yeah.
Oh no, sorry.
Okay. Let me.
Try for a paraphrase.
Oh yeah. Sense making.
You're like, in ordinary logic, things are just like, a statement is just like true or false. But in the real world, it's more like, I have a statement, and then depending on where I put it, like in this context or in that context, with this new knowledge or that new knowledge, it can like have different implications or something like that?
Yeah. I mean, I think even in ordinary logic, like there are certain contexts in which, I guess it's a particular property of that structure that when you add more premises, that you strictly get more consequences, and you have this transitivity. So this is maybe about the structure of that. In both logical and non-logical settings, you have sets of things you can say and moves that are good to go from one to another. And it's a property of logical vocabularies that you satisfy these structural properties. But clearly that's not how material concepts work.
It's a penguin. I
Yeah.
get different implications
Yeah.
or something like that.
And if you
Less in particular.
Yeah, and if you asked, your 2-year-old daughter, like, do birds fly? And the daughter, and she says yes. You're like, yes, good job. That is actually a good move to make, and you shouldn't. You didn't actually. If they said no, it wouldn't be that they were right for the wrong reason. They don't know. They don't know bird. Okay, so So I was just talking about a set of things you can say and a notion of a good move from one set of claimables to another. So this is formalized. Our main object of study is an implication frame. So an implication frame is formally just a set called a lexicon. It's a set of claimables. And a subset called I of equivalently the power set of L squared or the power set of L plus L. And so this is some notation. We're going to use like squiggly turnstile to talk about what is in this set I. So we could write that with like the pair of sets, as in A, B, and then C would be A, B, squiggly C. Alternatively, we could use this more monoid notation, which is coming from the fact that we could have positive signed claimables and negatively signed claimables. That would be this claimable is being asserted versus in the premises versus the conclusions. So these are all equivalent things, saying A, B, squiggly C, A plus B plus C minus in I. We're going to call empty, squiggly, empty 0. And this whole space, all of this, given a lexicon, all the sequence you could make out of that is just going to be S. And so what does squiggly actually mean? Well, squiggly is that, one way of interpreting that is that it's out of bounds to reject everything in delta and accept everything in gamma. And so we're thinking of the left-hand side as acceptance and the right-hand side as rejection. And what this has the effect of is it means that commas on the left-hand side are kind of like conjunctions, and commas on the right-hand side are like disjunctions. So it's, if you're committed to everything on the left-hand side, you have to accept at least something on the right-hand side. So this is what squiggly means, and clearly if there's only one thing on the right-hand side, this is our normal single succedent turnstile where, given a bunch of premises, you're sort of obligated to a certain conclusion. But you get a lot more symmetry if you make this disjunctive on the right-hand side and you have multiple conclusions. But remembering it's disjunctive, not conjunctive. And also, if the right-hand side was empty and you had gamma squiggly nothing, this is saying that it's out of bounds, it's incoherent to accept everything in gamma. So let's see an example, and I want to ease us into it with a fun, nice monotonic example, because this is supposed to be very fluid between logical and non-logical and all mixtures of concepts. So there is a particular lexicon of well-formed formulas of first-order logic with some particular signature, and so take that to be the lexicon. And then we can just look at what sorts of sequence follow. And it turns out that P, R is symmetric, RAB, squiggly, RBA, and Q. And in particular, we can ignore P and Q because that R is symmetric means that it's out of bounds to reject RBA, but accept that R is symmetric and RAB. But it is a property of logical vocabulary that you can just throw in other things on the left-hand side and throw in other things on the right-hand side. It's not going to change the fact that it's out of bounds to reject everything over here and accept everything over there. So monotonicity is this idea that I can throw in arbitrary things on either side of the squiggly turnstile. I'm never going to turn a good sequent into a bad one. And also, here's an example of a incoherence. And also, this is a good opportunity to say that the principle of explosion, which I think is just like embarrassing, because if you try to like show logic to someone, they go, "What? A contradiction means everything?" That's clearly not how. In real life, contradictions actually point us to like particular directions that we should go to like fix them. But formally, you get anything goes. And so you can see that if I can arbitrarily add stuff to either side of this, if I just add a singleton anything to this right-hand side, we're showing how P, not P, squiggly, any particular thing we want. So monotonicity is really responsible for this principle of explosion. Now let me just show another example that is no longer a logical example. Because, yeah, this notion of an implication frame is very flexible. Just imagine some context where, some social context where it could be English speakers, it could be upper middle class, Spanish speakers, it could be anything. The example I have in mind is I'm on a phone call with my mom, and I tell her that Zazzles is a cat, and now there's two sentences in this lexicon we're going to consider. That Zazzles has 4 legs, and that Zazzles has lost a leg in an accident. So absent any other context, it is a good move to infer that Zazzles has 4 legs, given that this background context that we both know Zazzles is a cat. It's also a good inference or sequent to go and say that it's out of bounds to reject both of these. The most interesting square in this whole grid is this one. This one is saying, given as a premise, Zazzles lost a leg in an accident, it doesn't follow that Zazzles has 4 legs. So it's out of bounds. It's not out of bounds to reject Zazzles has 4 legs while accepting Zazzles has lost a leg in an accident. So this is our first example of non-monotonicity. We've added a premise, and we've turned something that was a good sequent into a bad sequent. So the same framework can cover both of these scenarios. So now I'm going to start building off of this. But do people feel like they have a good understanding of what an implication frame is? The set and this distinguished subset of the possible sequence you can build out of it. Yeah.
So you don't have any axioms on your implication frames? Like,
no.
It doesn't have to satisfy.
Yeah, and let me, I think I maybe wrote somewhere.
Under the example you mentioned, containment.
Yeah, okay. So containment is this property an implication frame can have, which is that if you have overlap between the left-hand and the right-hand side, that it's automatically a good sequent, which is to say it's incoherent to simultaneously accept and reject one and the same proposition. And so often, even in our ordinary language material concepts, that is actually a nice thing to assume. Our definition doesn't enforce it, and honestly, I don't feel inclined to enforce it because sometimes whether two things are the same is precisely what's at issue, and you don't want to sort of bake that in and sort of irreparably be committed to that. So I think trying to be, as we'll see later, the purpose of logic is to try to make explicit these implication frames. And you don't want your formal apparatus for studying implication frames to restrict which ones you can look at and force them to be certain ways. So I think the fewer constraints we have, better. Sometimes some formal properties actually require assuming this, but I don't think I'll get into any of those. Great. So where do we go from here? Well, it turns out, given any set L, that there is a fun Quantale that we can build with it. This doesn't use the incompatible subset thing at all. So this is just purely given some set. I have this space of the power set of L plus L. And there's a Quantale, which is the power set of S, which is to say my objects, it's a poset. My objects are sets of implications. My tensor product is taking two sets of implications and taking their pointwise product and unioning them together. There's an internal HOM. And in particular, this will be relevant that it's atomistic and co-atomistic. So atomistic means that I've got all my singleton sets, and I can generate the rest of the lattice by just taking joins of those. And co-atomistic is the dual. So we have this Quantale, and you could think of this as like a syntactic category. Yeah?
Sorry, I just want to make sure. So can I, in the Zazzle example,
Yeah.
L is A and B?
Yep.
The set of A and B. Okay, and S is...
Yeah. S is like A plus A minus A plus A minus B minus is an element of it. 0 is an element of S.
Do you mean times? Or am I making it very silly?
Times.
PL times L?
No, it's PL squared. So each axis here is P of L. So PL squared is, so each
Okay.
element of here is an element of S. Yeah. And I'm telling you whether it's in I or not.
Yeah. Okay.
So now we can talk about sets of these things. So I've got, maybe this one, this one, this one, and this one, or just that one.
Okay, so I should think about like the elements of PS as like possible implication frames.
It turns out that I is an element of PS. Yeah. So you could think of those as like, oh, these are all the possible incoherent things. But maybe we should think of it as like, these are the sets of things that you can say. So I can say certain implication. Like I can say certain sequence. Like I can say that A squiggly A B, and I can also have sets of those things. We'll see where this comes up. So so this poset of all the things that you can say, including like sets of these sequence. And now what's interesting is that there is a self-adjunction. So there's a functor from QL. This is our Quantale Q. There's a functor from QL to QL op, which is now it depends on this I. We're going to take the internal HOM into I. And this actually it's a left adjoint to itself. So this is cool that you have something like that. And I want to say, like, what does this functor even mean? Like, what's the meaning of taking asterisk? And there's actually a very nice sort of semantics we can give it, or understanding, which is that, if we had a singleton set of gamma squiggly delta, what is gamma squiggly delta star? Well, we can think of it as the range of subjunctive robustness of that implication. So what does that mean? It means gamma squiggly delta may not be a good implication, but in certain contexts, for example, the context of theta squiggly lambda, it is a good implication. And so actually the set of all of these contexts in which, in that background context of theta squiggly lambda, that it is a good implication, that's what star is telling you. It's telling you all the conditions in which adding in my implication makes it a good implication.
Wait, and is that, did you define HOM just above, and is that like exactly what you said HOM is
Yeah.
a second ago? I just didn't actually
Yeah.
that. Yeah.
So if B is I, and we're taking A to be a singleton, then this is just all the x's for which if I union x, I get something that is a good implication. And the more things that I add to my set, then it's just intersecting, it's just adding constraints. So you could think of this sort of like as truth conditions intersecting. Like if I say, oh, I need to be in the range of subjunctive robustness of gamma squiggly delta and also theta squiggly pi. But so we can just generalize this intuition of range of subjunctive robustness to a set of implications by just intersecting them all. And that's what the definition of internal HOM gives you.
Can I ask really quickly,
Yeah.
what does coatomic mean again?
That means, like, imagine in like the power set lattice, you have all of the sets that are just missing one element.
Okay,
I can, yeah,
you can
meet them together and get everything else. Cool. All right. So now, the star autonomous category of facts. Sorry for just layering on definitions without payoff yet.
Can I try something?
Yeah,
Do you
yeah.
have an example in your Zazzle example? I like your Zazzle example.
Yeah.
I feel like it helps me really understand what you meant.
Cool. I have more Zazzles. Zazzles rolls.
Oh, I love Zazzle.
So yeah, so we can consider if this is 0, empty, squiggly, empty, and we consider what is the range of subjunctive robustness of that? What is the set, nothing, squiggly, nothing, star? Well, these are all of the implications for which if I add nothing to it, it is a good implication. Well, that just is the set I. But suddenly that's a nice, cute case, but the rest of the stuff is not as cute. Certainly, so we can take, this is why I decided to split screen, actually, for this very moment, where I can pull up both Zazzles at the same time. OK. So the most interesting thing is right here, because we're looking at what is the range of subjunctive robustness of just squiggly A.
And A was right.
A was that the cat had 4 legs. And so the question is, when we add in A minus, which is A as a conclusion, what things become good? And it turns out adding A minus to 0 moves it over 1. And adding A minus to something here is kind of like a fixed point. It doesn't change anything. So 0 is in this range of subjunctive robustness for the sequent squiggly A, or A minus. But it turns out B plus is not in that thing, because if I add A to it, it keeps me, I'm still a bad implication. And even B plus A minus, or B squiggly A, if you add A as a conclusion to that, it doesn't change it at all. So these are the 2 elements. These are the only 2 elements in which if you add A to it, it does not become a good implication.
Wait, what? Sorry, I get that if I B plus.
Yeah.
Oh, I see.
Yeah, so B squiggly A is not in this. And B is not in this either, but everything else is. Everything else in S. OK, so that's just like one computation. You could make that for all of them. It's actually interesting. This is the one example of monotonicity, and it's the one example in which I can't express this as like the complement of a power set. But regardless, the other ones you could sort of express as S complement some power set, and that's related to it being monotonic. But So yeah, so we have all of these. This table is basically telling you what are all of the values of for some singleton set, some singleton implication, what is the star of that? And it turns out that that's actually all you need because of this atomic business. All the other possible roles that you could have, all the possible values of something star is going to be just the meets, the intersections of these things. Yeah.
I can't figure out why this question is relevant. What are the boxes around?
Yeah. Sorry, this is a good question. So I tried to demarcate which check marks are just enforced by containment, and those are basically the not interesting ones. So these ones kind of come for free if you're trying to be normal presenting. But the boxes are really up for grabs. You don't, there's I guess 2 to the 8th like possible 2-bearer implication frames that satisfy containment. And so the conceptual contents of A and B are going to determine which one you're in. Okay, so I jumped a little ahead of that because I haven't told you like what a role is, what an implicational role, but an implicational role is just the value of star for something. It's telling you how does this sequent or set of sequence actually interact with the rest of the world. And hopefully this feels very categorical to you because these bearers, A and B, we actually don't have, if we go to the logic example, the implication frame doesn't actually see the internal structure of this. This is just an element of a set L to it. It doesn't, all it knows about this thing is what things it combines with to make good implications or not. So this is, I feel, a very relational thinking kind of approach because we're characterizing what this thing is in terms of how it interacts with all the other claimables. Okay, so I jumped a little ahead, but it was also good. I was about to talk about this star autonomous category of facts. So I should say there's a lot of prior work up to this point because
You didn't say anything about facts yet, I don't think.
yeah.
Didn't you skip a little bit?
Oh, did I? Oh, yes, I did. This was supposed to be collapsed. Yeah. So I introduced this Quantale Q. I said that there's this self-adjunction, and now I want to say that if you not every possible element of P to the S, which are just sets of candidate implications, is the value of, it's not a role. Not every element of this is a role. Some subset of these are roles. Because remember, we have, maybe this figure could be made bigger. I don't think so. There's this lattice here of possible roles, and there's this sort of dual lattice in QOP, which is sending everything to its star. But not every element of QOP needs to be hit is in the image of this. And so basically, if we restrict our attention to just the elements which are in the image of that adjunction, this functor star, then this is something that Girard calls facts, and he uses this as a semantics for linear logic because you can essentially get a star autonomous category out of this, and you can interpret linear logic. Our story will diverge from Girard's story, and I'll say a little bit about the relationship between the two at the end. Essentially, he uses star to codify negation, which is kind of a bad thing because it's letting logic enter too early into the story. So, this notion of negation is sort of conceptually prior to the notion of a fact, which should not be the case. You'll see later that logic sort of comes after our notion of semantics to sort of describe the semantics. But anyway, so we have this category of facts, and it's a reflective sub-post set of Q. It has all joins, all meets. It's co-atomistic because before we had something that was atomistic and we preserved all joins, which means we preserve all meets, and we have these co-atoms at the top. Hot off the presses, but I'm talking to Kevin about whether or not this thing is actually a quantale. But it's nice when that's true, but I don't actually use that fact. Yeah.
Can we do facts in Zazzle? I'm
Yeah, I mean, so yeah, that's these things are all facts. So any
Think of the objects as facts.
the values of star of something are facts, and any intersection of these four things is a fact.
Okay, could you explain why, like, S set minus, the one we generated?
This was the one that we talked about. Yeah.
What fact is that?
Like, why is it called a fact?
Yeah.
Why is that word?
Yeah, I mean, so why did Girard call these facts? Well, because I mean, Girard is trying to find, do some sort of model theory for linear logic and saying, well, what sorts of semantic interpretants can I give things like, I have propositions A and B, and A and B, and yada, yada, yada. And so what do I actually assign to the value of A or to the value of B, sort of as, like, you start off by assigning these primitives, and then he'll tell you what you should assign A and B, a sort of truth, the sort of recursive semantics. And so the objects of assignment for these things are the facts. So you don't get, so if you don't restrict to the star, the category, sorry, if you don't restrict to the image of this, you don't have the star autonomous category. So you don't have the structure that you need. So they're facts because they're the things, the semantics that Girard's formalism assigns to sort of propositions.
Oh, he's like, what does A even mean?
It means something star. And so.
In this case, it means the collection of contexts in which A becomes good.
Yeah, I mean, Girard doesn't think of it that, I mean, it's hard to say what we think. But yeah, from my perspective, that's what we should think of star as. It's giving a sort of implicational role of something. And if you're an inferentialist and you think what something means is constituted by its interactions with other concepts, then that is actually a good target for semantics, right?
Wait, can I try it? So, like, A minus, or sorry, that set that I was pointing to.
Yeah.
Is a fact. It's like the fact that we could have the result. Zazzle has 4 legs or something. Sorry, I'm trying too hard for something.
Yeah, it's the role that squiggly A, the sort of sentence, squiggly A or sequent plays. So and we're identifying that role with all of the contexts in which that is a good thing to say, or it's in bounds. So yeah, I mean, fact was not my word. I'm just using it because to draw the connection to stuff that is real and exists.
You mean draw the connection to the literature?
Literature, yeah. That's equivalent. Okay. Maybe, so there's also like all these facts about facts that we could have. Maybe these properties will be useful, but just to say that there are a lot of things you can say and start proving things using these facts, and a lot of these sort of come from the fact that like this fact, this claim here is true because star is a left adjoint, so you're going to convert joins into meets in the joins into joins, which are meets in the opposite category. Anyway, so a lot of these things just sort of fall out of thinking of it as an adjunction. I'll also say that we can sometimes think of the opposite of this category of facts, and I'll call that R, the category of roles. My notes might be inconsistent because I'm unsure whether I want to minimize the number of ops, and so I'm not sure whether it's more helpful to think about this category of facts or this poset of fact opt. But when it's fact opt, then we have our morphisms are actually when containment is in the reverse direction. Our joins are intersections. It's an atomistic lattice now, not a co-atomistic lattice. We have this monoidal product, which will actually be really useful in the semantics if I have time to get to that. I'm not sure if it's a star autonomous category. I think the conclusion was the opposite of a star autonomous category is not necessarily one. Anyway, let me try to move on to some of the punch lines. So logical expressivism, what is this about? So as we were just talking about, inferentialist semantics is this philosophy of language perspective which says that we should understand meaning as determined by inferential roles. And there's certainly one scenario in which everyone, no matter what your stripes are, you're going to agree that the certain concepts are best understood this way. So take logical conjunction. We have these introduction and elimination rules for logical conjunction, and we think that if someone knew how to navigate these moves, you could think of these as maybe conversational moves or formal moves. If you know how to navigate these sequent rules, you understand logical conjunction. I don't need to map that into some model theoretic picture or something. And so the more radical position is that even our material concepts can be understood this way. So it is red is incompatible with it is green in the background context of it's monochromatic. But it's scarlet entails it's red, but maybe in most, but maybe not all contexts. And so the idea is trying to understand what it is red as a statement means in terms of this network, and very analogously to this. And so as we mentioned already, then we might consider that our semantic assignments, these little bracket things, are going to be assigning inferential roles. So this gets to the definition of an interpretation function. So we're finally getting into, I've only talked about objects so far, and you should be thinking, what are morphisms? So here's something that could be a good morphism. An interpretation function is going between two implication frames, and it's going to send signed bearers, so LA plus and LA minus, to roles in the codomain. So I could get into it, but maybe you have to take me at face value that it's not the case that we can just assign our atomic sentences a single role, but you actually need to say what role does this play as a premise and what role does this play as a conclusion. In the non-monotonic case, those two actually need to be independent. But so taking that at face value, we can now interpret sentences. So yes, we've got A, we've got B, and so we've got sentences in A, and we're sending them to roles in B, or pairs of roles in B. Well, we actually want to interpret entire squigglies in B, and we do that using this monoidal product. And so this corresponds to, in Girard's linear logic, as par. And in fact, when Girard is interpreting sequence with multiple propositions in them, he uses par to combine them in his model theory. So this is the natural way of interpreting gamma delta, is to just par everything. You're parring the premissory roles of gamma, of all the little gammas, and the conclusory roles of all the deltas. So we now have a function from S of A to R of B. And so we have the role. Now we should be thinking about how do we further lift this function to roles. So I have, this is my category of roles. So I have A plus star and B plus star dot dot dot, A minus B plus star dot 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 I. And so this issue of like atomicity is saying that everything else in my category of roles is just some sort of meat of these atoms. And these atoms are fully determined by what are the roles of all of these atomic sequence. And this I is just 0 star. So one thing that we can do is say, well, if I want to lift this to the meat of two roles, then I just make sure that I preserve joins. So just do the obvious thing for all these complicated things. And so let's frame it in this question, because I actually spent a lot of time trying to figure out, is this notion of an interpretation function even associative? And if you start stacking like 3 levels of these monoidal products, it becomes actually like quite hard to see. But if we think of it as any interpretation function which is sending bearers of A to roles in B is actually secretly just a presentation of a join semilattice morphism. So I can uniquely factor one of these things into a morphism like that. Well, then I can just really compose in this category. And whenever I want to have an interpretation function, I would just like precompose with R. So this is definitely associative. And basically, we're looking at a faithful functor into this. So there's the category of all of the join semilattices. And we're not looking at all the morphisms between them. We're looking at some of them. Yeah.
Which one?
Yeah. So all join semilattice morphisms are going to send the atoms somewhere, and everything else is determined by the joins, right? And we have this rule, which was this interpretation function of sequence, which is that given a complex, so if this is equal to the monoidal product of two other atoms, then it is forced to go wherever that formula says it's forced to go. So if I didn't have this constraint, it would just simply be a full subcategory of join semilattice. But there is this constraint that how we interpret sequence. So I'm not free. I'm not free to send this wherever I want. Yeah, but the monoidal product does not play nicely with. Yeah.
That doesn't need.
Okay. Sorry, Sophie seemed to.
Yeah, I want more Zazzle. So like.
More Zazzle. Oh no.
I
Yeah.
don't know. I feel like I don't know how to interpret an interpretation function yet.
Yeah. So the idea is, yeah, it's very hard because of these power sets of power sets, all the examples blow up as soon as you have more than two claimables, and it becomes hard to express like lots of interesting things in a finite space. But the idea is that, let's see. Okay. So the idea is that if I have, let's say we have Zazzles as our implication frame here, and then we have, let's just say, some world. Okay, so we have, we're going to interpret the sentence. So someone says like, oh, what do you mean by Zazzles has 4 legs? I'm going to interpret what that means in some other implication frame. And the idea is that, I'll just show the property here. It would be really nice if we had this property that like, this is a good sequent in my domain if and only if the sequent, my interpretation of that sequent in this other domain is a good sequent. So, sorry, this should be a subset operation, yeah. So the idea is that one way that we can ground, like, I think a fair objection to like, what are these material implication frames? It's like, where does that squiggly even come from? Is it just made up? And one way that we can justify what it is by pointing to another one and saying, well, if we interpret those in this other one, you have to take something at face value. Like, but if you trust this other implication frame, I can give you an interpretation of what I'm saying and show you how my squiggly is induced by this other squiggly. So if you had a sort of world model that was like more robust than these two sentences, but includes things like, you know, cars and ambulances and veterinarians and whatnot, and then you might be able to actually derive that as like, oh, these are good implications, like that it follows.
So you're sending the claim Zazzle has 4 legs to something roughly. Okay, the world is everything that is the case, and like all of the possible states of the world in which.
Yeah. So actually, this comes into the end that this was actually, so a lot of this work is like trying to reconstruct this work in this philosophy book that was not done very categorically, and try to show why its constructions are like actually natural, not just sort of made up. And one really big result that they have is that there is a generalization of possible world semantics called Truthmaker semantics. Essentially, it was invented because 1 + 1 = 2 and 3 is a prime number mean different things, but they're true in all the same possible worlds. So if you want like an extensional semantics, you can't just like say, oh, two things mean the same thing if they're true in all the same possible worlds. So it's called hyperintentional. And the way that this like really like semantic, I want to say, in the sense of like I'm building a model of the world and I'm interpreting things in terms of like these sets. So it does this by saying there are truth makers and false makers and certain combinations of those are states of the world. You can combine states of the world, and certain states of the world are impossible, just like, you know, maybe impossible by the laws of physics, maybe metaphysically impossible. And one of the really interesting things in this book was to show that actually this is structurally completely identical to the notion of an interpretation frame. The idea that I could have truth makers, A, B, C, squiggly, D, E, F, and that the truth makers of A, B, C combined with the false makers of D, E, F, if that is an impossible state, that's basically word for word identical to the idea that like, oh, the accepting A, B, C and denying D, E, F is an incoherent, you know, is an incompatible or incoherent state, an incoherent thing you can do. So it turns out that even this sort of like very semantic world model-y thing, which is generalizing possible world semantics, which we accept as like, oh, that's sort of like building a model of the world, like first order logic style, that there's actually, I don't need to think of this as just like a bunch of claims that people are making that the world is all the set of facts or whatever tractata stuff you're doing. But you can actually understand this as like a bona fide model of the world in the way that people traditionally think of it. And it will have the same structure as an implication frame, so I can actually have interpretations into it. So I think this is really good, and this is the move that I consider to be analogous to what category theory does when it puts syntax and semantics in the same playing field as like objects in the same category. That we've shown that there's a common structure that allows us to relate, you know, where the notion of incompatibility is that it is normatively out of bounds to assert these things while rejecting these things, and then you have the sort of realist picture of like these are possible states and these are possible states, and that the truth makers of these states and the false makers of these are impossible in a metaphysical sense. The idea that those have the same structure is what allows you to actually do some, I think, interesting things. And maybe this was all sort of spun off of like, what is an interpretation function of Zazzle's? And so you could interpret what this Zazzle's talk in terms of some other language game that people are playing, but you could also try interpreting it into some actual bona fide model of the world where it's a little ambiguous what these states are in the truth maker semantics. It's hard to communicate. It's not ambiguous. Yeah, I'm sorry. If I want interpretation functions to be cool. I can map my sentences in one language to meanings in another, where meaning, we said, was the role that something plays. And so, yeah, I think there's a lot of currency that you can get by considering the category of, and I'm almost out of time, so maybe I'll try wrapping up. I think there's a lot of currency you can gain out of understanding the category of these things because, one, it's like relating different perspectives to each other. Two, what are some things that I want to say? Well, I didn't get to talk about logical elaboration. So I didn't get to talk to this logical expressivist idea that we can actually, that given these sentences A and B, that we can give a semantics to A and B. And now this is not like, this is and that is actually available to us. It's not like the internal and of that first order logic example. So basically what they do in this book is like show that we can give a recursive functional truth, a recursive semantics where we're assigning given assignments of roles to A and B, we can assign roles to the logically complex sentences. And this has very nice properties and you can recover classical logic if your underlying interpretation frame was monotonic and intransitive. So you sort of, and basically this perspective also allows you to unify all sorts of like three-valued logics and paraconsistent logics. You can see how basically all the things that we call logics are essentially ways of making explicit specific subclasses of interpretation frames. Like classical logic can't make explicit a non-monotonic implication frame. And what they do in the book is provide a universal logic, which is something that can fully explicate any interpretation frame given the definition of implication frame. So that is like a kind of universality that I think is really cool. It's sort of, I haven't had time to sort of make precise what this notion of logical explication is, but the idea is, you know, just to take one example, let's say maybe logical conjunction, you know, to introduce logical conjunction is to make explicit this fact. So these are double lines if and only ifs. So A gamma, AB, I'm using a triangle now just to distinguish from the turnstile for various reasons. This is now a sequent calculus. But basically this is saying that and, the role of and, actually what it does is it makes explicit commas on the left-hand side of the turnstile. And the role of or makes explicit commas on the right-hand side of the turnstile. And the role of implies is to make sense of be on opposite sides of the turnstile. The role of not is to switch from one side to the other side of the turnstile. So the idea is that logical vocabulary allows you to put in the form of a claimable what the structure of that implication, what was purely kind of the background structure of these claimables. So you can say that if Zazzle has broken a leg, has lost a leg, then it's not true that Zazzle's has 4 legs. That you can put that into a claimable form that was already implicit in the implication frame, but now it's a sentence that you can say. So that's sort of what the role of logic is and explains why it helps us coordinate, that it's taking these practices and putting them into sentences so that you can then, maybe you can challenge and say, I don't think it's a good idea that this follows from that. Maybe we should change our implication frame. But if you can't if you can't describe the implication frame, then you can't do that kind of corrective action. So yeah, I guess I didn't have, there's a lot to say about dynamics. Woo, there's a 2-cell and a double category. Whoa, what's that about? And there are lots of technical questions. One, I think the big one I'll leave you with is that this notion of sending sentences here to roles in here seems very Kleisli-like, right? I'm sending simple things here to fancy things over here. And I think there are plausible notions of morphisms from implication frames to some category of roles and backwards. But there's a lot of details to be what are those categories and is it actually an adjoint so that we get a monad out of it. So these are the things that I want to work on. Also, these formulas for the semantics of conjunction and disjunction, these are kind of ugly formulas, and it would be nice if they were just like the categorical product and coproduct in some category of pairs of roles or something. So that seems like something that morally should shake out, but has not yet shook out. And yeah, I think I'm excited to try to generalize this to predicate logic. So the idea is that somehow, for all xy, p of x implies q of yx is making explicit some feature of a bunch of things that can be said, and making that precise in the same way that and or and not are making features explicit. It gets into, I think, a lot of symmetries, and there's some interesting math to be done there. Anyway, thanks. I hope this was intriguing, at least. Yeah, Dana.
Allow me 2 very, 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 very quick questions. In the beginning, you were emphasizing change of concepts, and I lost a little bit when the change takes place.
Yeah.
Let me say the other thing there. Back in the days when linear logic was introduced, people emphasized over and over again that it was managing resources. And, and you didn't seem to use that kind of metaphor.
Yeah.
Here.
I
Is there a connection?
not between the 2 questions, but they're both good questions.
No, I meant, is there a connection between what you're doing with the way people used to talk about resources?
Yeah, so that's another open question of this was assuming we had a set of claimables on one side and a set on the other. we could probably generalize that with another monad, like the list monad, where we actually care about the order and we care about how many of each thing we have. And so that might, parameterizing this all by a monad and set might be a good idea to like really get some power out of this. So this was baking. I was arguing against baking in monotonicity, but I baked in, swapping and, contraction. So yeah, you shouldn't have to do that. This was just the sort of simplest presentation. So yeah, so that is what I was talking about should be generic over those sorts of questions. But I just made the assumption that we had unlimited resources. And then the question about change, I think, is a fair one because the question is, how do we think of dynamics here? And I guess that was maybe where the double category came in, of talking about given some interpretation of our sentences in something that we take to be true, that sort of that induces a dynamics on not only what we take to be true over here, what we take to be a good implication, but also on the model itself. And yeah, I guess there's a lot to be said about how monotonicity makes non-monotonicity makes it possible to say, for example, there's an issue when you try to define things by truth conditions, which is that people before 1900, scientists never could refer to electrons because they defined electrons in a certain way, and then we found out nothing actually satisfies that definition, so they weren't referring to anything by their theories. And the idea that you can add context, that they could have still been latching on to a real thing, but just given the context of what they had, other things followed from it, is a notion of conceptual content. It's a way, it's only in retrospect, but in retrospect we see that they were, that the concept, let's see, yeah, the idea is that you're not forced into this idea that they were contradicting themselves and therefore implying everything. And so this vocabulary allows you to make sense of the history of what happened in a way that is actually showing how the concept evolved. But yeah, I didn't have time to talk about dynamics, sorry.
So wait, yeah, I guess just to build off of that, I guess is the idea of trying to make some statement of the shape of the constraints that are present for logical entities for this,
Mm-hmm.
the ones that are sort of satisfying those are the ones that structurally would be required to support some dynamic characteristic on the larger sort of possibilities that are present in implication frames. In order for the dynamics to work out in such a way as a collective, there has to be a constraint on the shape of the ones that are your logic for that enables the dynamics to evolve in that particular way.
Maybe we'll have to talk about that at lunch. But yeah, certainly taking something to be monotonically true, taking A to monotonically entail B, is making a stance that no matter what happens in the future, I'm never going to give this up.
Right.
And you're still allowed to you're still allowed to express that. But I honestly don't think that's what people mean when they say things follow from other things. And so this is but it is important. In math and science that we can take that to be at least we can work in a sort of clean room temporarily, locally, until there's some paradigm shift, and work with a fixed frame and negotiate the content. Yeah, Brendan?
I'm curious what your thoughts are on construction of software representations as a communication artifact for these ideas, but also how quickly they become useful.
Yeah.
So first, this Zazzle thing was kind of difficult in words.
Yeah.
And hard to parse. But I imagine if you sort of codified that and people would probe it, we could have actually got a bit more clarity.
Yeah, I agree. I've written some basic code that basically searches for it will compute asterisk for things, and it will search for morphisms between these things. And even though this seems like a lot of data because you've got power sets of power sets, if you use bit sets, you can sort of compress big power sets into a few bytes. So So I haven't really had time to like work it out, so I have a working demo. But yeah, I think that, you know, I would want to be able to basically like take co-products of implication frames and unite our perspectives and show how we can map my beliefs onto yours in various ways in a way that is, yeah, analogous to what we do with CatLab.
Do you see this being practical in near terms of like, can you, with these small examples, can people effectively try and negotiate the rules of the frame of inference that they're kind of
Yeah, that's a good question, because that is the, I think this is why inferentialism has trouble with popularity, because you can't really understand the meaning of something. You can't have a concept without having many, many, many concepts. And the sort of atomistic bottom-up picture says, oh no, I can know what it means to be a horse just by these truth conditions I'm putting on horse. And that's convenient, but yeah, so the question is it really impractical how many other concepts that you need in order to do something non-trivial with this? I'm not sure, but I think that is a good question. I think when I think of applications, I think of maybe like the discourse graphs of actually making that more rigorous instead of just informal language. And I do wonder whether or not, like, you know, if we're actually computing with these things, you know, you don't want to work with, you know, the full expanded version. Like you want to be, this is why I want to categorify this, because you want to be working with limits and co-limits so that you're always working with presentations of these things as opposed to the full data, which is obviously immense. Yeah, anyway, thank you.
It's obviously